Hello, everybody. In this session, we will understand the rest of the instructions in the category of memory reference instructions. In the previous session, we discussed about the BSA, that is branch and save the return address. When a procedure is going to call another procedure, rather, when a routine is going to call another routine, which is called as a subroutine for the current routine, then we are going to use BSA, which is going to serve as a call instruction in the high level language. Similarly, we also do have one more instruction called BUN. What is BUN? BUN is an equivalent instruction to jump instruction. Let me show you. I'm going to take the same example. That is, in the 23rd address, rather than BSA, I do have an instruction which is BUN. What is this BUN? BUN is a jump instruction. The difference between the call and a jump instruction is when a call instruction has been executed, then we are going to perform a branch to the subroutine. We'll branch to the subroutine, after which the subroutine gets executed. Finally, after the execution of the subroutine, we will branch back to the routine from which the subroutine has been called. Calling routine, called routine. Once after the call routine is executed, we must return back to the calling routine. But jump is different. Jump also performs a branch. That is, even when you execute a jump instruction also, you're going to take a branch. But you don't need to return. This is simply jumping. We are skipping some instructions. You know what is jump? During the jump, we will simply skip a few instructions and we will directly start executing the instruction which is provided within the jump instruction. For an example here, this is BUN. BUN is an equivalent instruction to jump. BUN 450 means you can skip all the intermediate instruction till 450 and you can directly start with the execution of the 450th instruction. This is the difference between BSA and BUN. When you perform BSA, you are going to branch, finally you are going to return. When you execute BUN, simply you are going to branch, but you will never return because simply we are skipping and jumping. Now, let us understand one more important thing when you execute a call instruction. A call instruction, as it is associated with a return, first of all, we need to understand that the program counter value must be saved, right? Because unless we save the program counter value, there is no way we can return back to the previous routine which was suspended. For that, we need to save the program counter value. In the previous session, I told that the program counter value will be saved in the buffer. After executing the subroutine, we will go back to the buffer in which the program counter value has been saved. Taking this address, we will start resuming the previous routine which was suspended. Here, the thing that is needed to understand is where to save the program counter value. Because in the computer system, everything must be clearly specified. I simply told that is a buffer. I need to define this buffer to the CPU, where the CPU can actually store this program counter value before it is going to perform a call. This buffer provision is important. Here, you need to understand that this buffer is nothing but a stack. This buffer is just nothing but a stack, system stack. Okay, what is a stack? Now let us understand the stack superficially, because altogether stack will be completely explained in a different session. But let us understand, in a computer system, there are two kinds of stacks. One is CPU stack, one is memory stack. Memory stack. CPU stack is a stack which is designed and embedded to the CPU. Memory stack is a stack which is in the main memory. That is the difference. Now, every time when you perform a call, when you execute a BSA instruction, the next instruction's address, that is the program counter value, should be saved. Where? It is just nothing but within the stack of the CPU. You know that the CPU has a stack. So what we need to do is, before we branch to the subroutine, we will perform a push operation. That is, the program counter value will be pushed into the stack. Okay. Once after the subroutine has been executed, in order to return, we need to perform a pop operation which pops out the program counter value from the stack, taking which you will be able to resume the previous routine which was suspended. Once again, before you take a branch, you need to perform a push operation. What must be pushed? The program counter value should be pushed into the stack. Once after the subroutine has been executed, we must return. In order to return, what we need to do? We need to perform a pop operation which pops out the program counter value, taking the program counter value. Since this is the value from where the previous routine has been suspended, we need to start resuming the previous suspended routine. This is how call and return will be made. Steps will be as follows. High-level language call will be translated to a low-level language, the machine language instruction, corresponding instruction, that is BSA. BSA is branch and save the return address. That is, before branching, you should be able to save the return address. For that, what we need to do is, we'll simply push the program counter value into the stack. Okay. Then after call, we must return, right? For returning, what we'll do is, we will pop the program counter value out of the stack to resume the previous suspended routine. This is how call is going to be performed. The next and the final instruction within the category of the memory reference instruction is ISZ. ISZ, if you remember, that is 110. An opcode combination which is 110 signifies that the instruction is ISZ. ISZ stands for increment and skip if 0. Increment and skip if 0. What is increment and skip if 0? Let us understand how does it work. When there is an instruction called ISZ, rather, increment and skip if 0, the instruction look like this. You know that the most significant digit will be mode. Then the opcode bit combination will be 110. 110 will be followed by a memory address, let us say 250. 110 stands for ISZ. As it is ISZ, immediately we go to the operand. Where is the operand? Operand is specified at, located at the memory location 250. You just need to go to the memory location 250, collect the operand. Let us say the operand is equal to 40. ISZ stands for increment and skip if 0. You know that increment stands for we need to increment. What must be incremented? The operand must be incremented. What is the operand? The value which is available in the memory of 250, that is 40. This is our operand right now. So we need to perform an increment operation, that is 40 plus 1 we need to perform. Okay, 40 plus 1 is equal to 41. So increment operation has been performed. But the instruction has something else, that is increment and skip if 0. After incrementing, we need to compare if 41 is equal to 0 or not. Is 41 equal to 0? 41 is not equal to 0. So the condition fails. So we don't need to skip anything. Here, that is, what is skip if 0? First, we need to increment the operand. After incrementing, the value is equal to 0. We need to skip the next instruction. For an example, the current instruction is 23. For 23, the next instruction will be 24, which is specified in the program counter. Current instruction 23 is increment and skip if 0, that is 0, 110 followed by 250. Going to 250, collecting the operand, I have incremented and I got to a value which is 41. Then I compared it. If the 41 equal to 0, no, 41 is not equal to 0. If 41 is not equal to 0, I don't skip the next instruction. I will execute the next instruction. If the value is equal to 0, I will have to skip the next instruction. That is what increment and skip is 0. Increment the memory operand, after which if it is equal to 0, then you skip the next instruction. Otherwise, you don't skip the next instruction. Okay. For an example, the value under 250 is -1. If it is equal to -1, after incrementing -1 plus 1 will be equal to 0. Then the condition satisfies. Increment and skip the next instruction if the value is equal to 0. Next instruction will be obviously skipped because the incremented value is equal to 0. After incrementing the operand, we reached a value that is 0. As it is 0, we need to skip the next instruction. Once again, in a nutshell, if you actually can have a look at ISZ is going to increment an operand and checks if it is equal to 0. If it is equal to 0, it is going to skip the next instruction. If it is not equal to 0, it won't skip the next instruction. This is what increment and skip if 0. Once again, just have a look at what are all these instructions. You know that the first 7 opcodes signifies the memory reference instruction. 000 is end, 010 add, load, store, bun, bsa, isz. What is end? We are going to perform an AND operation between the memory operand which is specified in the instruction and the accumulator. Next one is add. We are going to perform an addition operation between the memory operand which is specified in the instruction and the accumulator. Load operation. Load operation transfers the contents of the memory operand that is specified within the instruction to the accumulator. Store operation transfers the contents of the accumulator to the address which is specified in the instruction. So the load operand, store operation, load operation and the store operation are going to perform two mutually disjointed and different operations. BUN, it is a corresponding and equivalent instruction to jump. BSA, it is a corresponding and equivalent instruction to call. ISZ, increment and skip if 0. We need to increment the memory operand that is specified within the instruction. If the incremented value is 0, then the next instruction will get skipped. Otherwise, it won't get skipped. Here, if you can actually have a look at BUN and BSA are interchanged. In this design, he just went for BUN before the BSA. But actually, in my design, I started designing the BSA initially, then I designed BUN. It is your call. Being a programmer, being a designer, this is completely your call. Which combination gets encoded to gets designed and given to which instruction, that purely depends on the designer. If you are a designer, if you want to use different combinations for these instructions, you're welcome. But you need to understand these instructions must be implemented within the processor, because every time when a high-level language instruction gets executed, corresponding one of these machine language instruction will always get executed. Okay, so this is all about memory reference instructions. In the next session, we'll start with register reference instructions. Thank you.